Alright, and we're back with our final two functions that we will graph. Obviously, a pretty gnarly exponential, and then we will delve into a rational function, iron out some kinks before closing the door on our curve sketching exploration. So, as I said before, first and foremost, try and start with your y-intercept. Oh, blue is going on me. F of 0 is clearly equal to 0. 0 times e to the 0, which is 1, will still yield you a 0. Next up would obviously be the first derivative, so we can identify any extrema and the increasing, decreasing behavior of the function. So, first times e to the second, that's not going to change, plus the second times e to the first, which we can factor as x plus 1 equal to 0. That will never happen. Therefore, this is our only critical point. And if we test, right, e to the 0 is 1, 0 plus 1 is positive, negative 2, that'll be a rational value, this will be negative, so we have negative, positive. Once again, we have a minimum value, and we also have from negative infinity to negative 1, decreasing, and negative 1 to positive infinity, increasing behavior of the function. Second derivative test will tell us any points of inflection and or concavity. So let's derive this. First times e to the second, e x times 1, plus the second times e to the first. We can once again factor out e to the x. 1 plus x plus 1 is 2 plus x, which is set equal to 0. Same situation that we had unfold here. This will never equal 0, therefore x equals negative 2 is a test point, which we replicate our first derivative test. So you pick f of negative 3. Negative 3 plus 2 is negative. Rational is negative. F of 0, 0 plus 2 is positive. E to 0 is 1. Therefore we have, yes, point of inflection. And we can substitute this back in if we wanted to. We're not really going to get a value though, because we'll have 2 times e squared. So I would just leave that be. But one thing we haven't talked about is, what the heck do we do about end behavior here? Well, remember, end behavior is nothing more than the limit as x approaches infinity and the limit as x approaches negative infinity of the function. So as x approaches infinity, so as this value is getting really, really large, both of these are also subsequently growing. So the function should shoot off into positive infinity as x gets larger and larger. But what happens here with negative infinity? Well, negative infinity is going to turn this, right, negative infinity times e to the negative infinity. This will turn into a 0. So we have an indeterminate form. Dun da da da! What comes into play now? L'Hopital's rule, which says if we have it, as long as it's written as a rational, we can derive it. So we have 1 negative e to the negative x. So that's really negative e to the x. And oops, I missed a step. No, I don't think so. Nope, something like that. Sorry. So we have the limit as x approaches infinity of 1 divided by negative e to the negative x, which subsequently will yield a 0. So if I were to graph this, which once again I have little to no room to do so, so I'm going to erase this. Right, I know as I'm going rightwards, we're going to go up here, leftwards, we're going to skim along 0. If I just substitute even in a negative value, I can see that a negative times a rational value, so I'm going to have negative outputs. So I'm actually going to start my graph around here. I'm having a minimum at this value, right? So -1 times e to the -1. So if this is -1, I know I'm going to do a little bit of a dip. I'm coming through a y-intercept of the origin, and I'm shooting up. Okay, once again, the graph is not our focus. It's all of the information that you can compile to inform the sketch of your graph. Minimum value, y-intercept, x-intercepts if it's a polynomial within reason, the increasing, decreasing behavior of the function. What else? The end behavior, the points of concavity, or not the points of inflection, the overall concavity of the graph. All of those pieces are now required, for lack of a better phrase. And let's just do one rational function, and that'll close us out. 3x plus 2 over 2x minus 4. So with rational functions, the first thing we want to identify are the undefined values. So x cannot equal 2, because that will give us a undefined function because the denominator is equal to 0, so that becomes our vertical asymptote. And x equals 3/2 becomes our horizontal asymptote, ratio of coefficients of the leading terms. And if we wanted to know the y-intercept, we can substitute in 0, goodbye, that's going to be -1/2. Right, boom, step 1 for rational functions. Step 2, take that derivative. It's going to be the quotient rule. Due to board space, you can work that out on your own. I'm going to tell you right now that it's -4 over x minus 2 squared. So, we run into a bit of an issue because x is not allowed to be 2. But we had said that we look for values that make the first derivative equal to 0 or undefined. However, we cannot say that x equals 2 is a critical point is not a critical point because it does not exist in the domain. So, what do we do then? This is a tough one. But is it? Notice, aside from x equals 2, if you substitute any value into here, regardless if it's negative or positive, the denominator will be positive because we have this even power. But our numerator is negative. So we can actually say that the first derivative is going to be less than 0 for all x aside from x equal to 2. So we should see decreasing behavior across the entire domain, -infinity to +infinity. Okay? We'll replicate this process though for the second derivative because we still need to check for inflection points and concavity. So I'm going to, because of board space. Now once again, okay, we don't want to call x equals 2 a point of inflection if it does satisfy the criteria, because once again, it does not exist in the domain, right? We have a vertical asymptote there. There are no defined values. There's no output at that value, okay? Right now, we're just checking for concavity. So, we can see that if we substitute in 0, we'll yield a negative value in the denominator and a positive in the numerator. So negative, and then if you replicate that process with a positive value. So yes, it could have been a point of inflection, but since it's not in the domain, it's nothing. But we do have concave down from negative infinity to 2, and concave up from 2 to infinity. So right, we have all this information, right? We're decreasing across the entire domain. We have our intervals of concavity. We have our asymptotes. We have our y-intercepts. What are we really missing? Behavior around the vertical asymptote. And that's a little easy. We're just looking at the limit as x approaches 2 from the right, and x approaches 2 from the left of the function. So pick one from the left. 1 will get you 3 plus 2 is 5. This is going to be negative, so I know that I'm going to be going towards negative infinity. The closer I get towards 2 from the left. And if I flip that, if I pick 3, it's going to be 6 plus 8 and 6 minus 4, which is 2. So positive infinity. So what is this graph going to look like? Well, I'm going to have a vertical asymptote at 2 and a horizontal asymptote at 1.5. Okay. Neither of these you need to sketch. Okay. You just need to make sure that you have them noted somewhere. Okay. I'm going to have decreasing behavior. So if from the right, as I approach 2, it's going to tend towards positive infinity, I'm going to come down and coast along that. And then if I have decreasing behavior but a horizontal asymptote here and a y-intercept of 0, negative 1/2, that means I should be crossing through the x-axis at some point. Now, if I specify, or somebody specifies, hey, you need to find the x-intercepts, well then, stinks, you gotta find the x-intercepts. It's pretty easy to find, because remember, x-intercepts have y values of 0. So set this bad boy equal to 0. The denominator will go away, so x equals negative 2/3. Negative 2/3. Okay? It's all about tying together all of this information that you've been honestly working on since you were a freshman in Algebra 1. But that's where we're actually going to conclude our exploration, and we will pick up in the next unit on integration. See you there.